Last time we finished off by looking into accessors and static. And we're gonna make use of that today, because we're finally gonna program an actual program that we're gonna compile and run. And maybe more than one. Before we do that, however, we have to discuss a few details. Nothing you don't really understand, nothing technically new, but a few quirks of how .NET operates. And for that, think about how your program is actually run. When you write a computer code, how does that translate into, I probably double click on an icon somewhere on my computer and it does something. How does that work? Well, at least on Windows, you would have an executable. Other operating systems, of course, have the same, just different names maybe. But you always have finished machine code that a computer can just execute directly. Remember our initial lessons about machine code and assembly and how we move up to higher level languages? Well, these executables are at the very low end, or at least they should be. Then how do we go from our high-level C# to machine level for the executable? We have a computer that translates the high-level language to the machine code, and that's the compiler. Also, something we discussed very early on. We just go in, well, not so simple steps in C# anymore, from abstract computer code that we've used so far to these are individual operations that the CPU can perform, like move a bit of memory around or add something in the ALU together, stuff like that. And special about .NET, which is the overarching framework for C#, we have a framework in the first place. What that means is, for many languages, for example, if you just write code in C instead of just C#, that's good old C, also very nice language by the way. Not a fan of C++, but pure C, nice. You would compile that and you would generate the executable directly, and the computer could run it. .NET, however, was, let's be very generous and say, inspired by Java, another programming language that oddly enough looks very similar to C#. At least it used to be very, very similar. So similar that you could copy paste the code and it would work. Pure coincidence, I'm sure. Like Microsoft had no shady business there at all. Like C#, not in any way a Microsoft product to maybe get rid of Java, build up some competition. Well, let's not get into that. What that means is, when we compile our C# program, when we go from high-level instructions down to machine code, we don't build machine code for our computer directly. So whenever you compile your C# program, you are compiling, but what you're generating is code for another made-up computer. Just how my initial CPU was just a program running on my computer and not an actual physical piece of electronic. With .NET, you have a special program running on your computer. And this special program is emulating a CPU in a way. Like you can translate instructions down to a sort of machine code, and that machine code is then executed. Well, actually it's more assembly, not machine code directly. But this assembly is then understood by this special program for .NET, and that will then run actual machine code on whatever device you're on. So you have this two-stage process. With other languages like C, or with many other languages, not just C, but that's just my favorite example right now because C, C#, whatever. You compile directly to the machine code for wherever you run your code, and you're done. Downside of that approach is you only can run on that one machine you compiled for. And different computer systems have different requirements, different ways of how they work, both in terms of how the actual machine, the hardware works, but also a bit earlier how the operating system works. Because in the end, you rely a lot in your programs on features of the operating system. Even if you intend to run it close to the metal, so to speak, if you run it directly on the CPU, there are still many functions you can't properly use without interacting with the operating system. And different operating systems work very differently. Even different versions of the same operating system can work very differently. So with a programming language that compiles directly to machine code for the end system that can be run directly, you have to compile it to different target systems. So common, something like I compile one for Windows and I compile one for Linux and maybe one for Mac and then maybe one for Android and stuff like that. And then of course different machines. This one is for a microcontroller, this one is for PC, this one is for a tablet, this one is for a toaster. You have to recreate the same program for different targets. Advantage here is that you specifically create code for that end product, for that machine, which makes it possible to optimize it for that one machine, which gives you a speed boost. Less resource used, very nice. Downside is you have to compile it for every machine, and you have to maybe change your code even a bit to make it compatible with each machine. There are things the compiler can't do on its own. And there are other languages, like C# and of course Java, which is, again, what it's kind of based on, where you don't compile for the end machine directly, you compile for a made-up machine, a runtime, which is running on the target systems. So this runtime is one singular program that still has to be optimized for each target system individually. So someone has to take care of that, but that gives you a universal endpoint, so to speak, that your one program can run on. So you make a two-stage approach, so you have a bit of optimization in terms of writing code and saving resources when targeting different systems. I'm not sure if that's quite clear. So instead of... Imagine I have a pretty shitty bike and I can't really drive on off-road. Like if it's a very nicely paved new street, no problem, I can just drive on that very nice, very comfortable. But if there are any potholes, I'm getting into trouble. If there's just mud, I probably get stuck. And so for these different roads, I might have to change the tires a bit, and well, that takes a bit of time. And the downside is then those tires might not work so well on the regular paved road anymore. That would be the classic approach. And with these frameworks, the one something like C#'s doing, someone is putting down a very standardized set of plates on top of the road, no matter what road it is, and you always drive on those plates. Like, maybe someone is rolling out a red carpet, sort of. So they have to kind of make sure that whatever they put down fits the road, so it doesn't sink into the mud. Maybe put in some flotation, maybe some softer materials, maybe puts down some rubber on a normal road so it's not moving around so much. That's their problem. We just get one standardized set of roads that we can use everywhere, as long as someone else puts down the plates. And these plates, that's our framework. And .NET, that comes in different flavors. The old system, that would be .NET Framework, literally framework, which stopped development at 4.8, I think 0.1 something. So you probably have that installed on your machine because it was always released with Windows. At least if you have a Windows machine, you probably have that because it was automatically added to your PC. There's also an non-Microsoft version, which is called Mono, which still exists, which is still used. So at some point in the past, you basically have .NET Framework running on a Windows PC and Mono on Linux. Then there was .NET Standard, which is not exactly a framework, but we'll get to that in due time. But that's a thing that exists. Just remember, for now, we don't develop for .NET Standard. Not really. And then, this is the confusing part. Microsoft, or the .NET Foundation, which, I mean, it's a Microsoft, whatever, introduced .NET Core, which was not as integrated into Windows, more freeform and open source. I'm not sure if it's open source. Honestly, I'm not sure about the state of .NET licenses right now. Should probably look that up. Doesn't really matter to my job. Well, anyway. .NET Core was developed for a while and has been renamed, so to speak, in new versions to just .NET. And when they did so, they basically retired .NET Framework as well. So the .NET Core line just replaced .NET Framework, and so now we have .NET. And the first .NET was .NET 5. So that was presumably to keep the version numbering easy. So if you went from .NET Framework 4.8 and you go to .NET 5, that makes more sense, even though they are very different products. So .NET is actually .NET Core, just renamed, and it's nothing like .NET Framework. Though there are many, many different libraries, something we talk about later, that attempt to recreate functions that we had in .NET Framework. Ooh, that's a lot. And all these frameworks run a kind of assembly, which we call the intermediate language, IL, which is what we compile our actual source code into. Wow, this was a long talking session. I should have probably written down the stuff. Might have been easier for you. Oh well. Now let's talk about compiling. When you start your program, what is the code that it will execute? What is the first line of code that it will run? Because remember how I always just write down some code. Like int a equals 5. There, just a line of code. That was enough for us to learn about C#. And sometimes I had an extra class, and I would call a method in that class and execute some more code like that. But this is not really possible in C#. We can never have just code on its own. Every piece of code we write has to be enclosed inside a method. This doesn't have a method. I wouldn't be able to compile this. And yeah, I know, newest versions do have ways to get around the boilerplate. We're not talking about that yet. Those are just syntax sugar. We talk about the basics, what's actually going on behind. And that's still not gone. You can just hide it now. So, save the comments, please. Every code we have has to be inside a method. Okay, so we create a method. Let's just use a void method. Void method. Well, let's be lazy method. We just call it method. Okay. Int a equals 5. So now we have a method that we could call to run our code. And in this code we can run other methods that do more code and can call even more methods to do more code. Alright? This is also not allowed on its own. A method can never be on its own. It always has to be in the context of a larger structure. like class or struct, or some other structures we are going to learn about in the future. But just imagine another structure around it, like class, some class, like that. Now we have actual valid code, source code. We have a class which can stand on its own, and in that is a method which we can just add to a class just fine. And in that we have source code with actual instructions for the computer to perform. Nice. Now let's add another class. Let's be creative and let's call it other. Maybe let's be more creative and call this method as well. Which we can do because it's a different class. We can reuse the same name in a different scope. Can even call this int a, just this time maybe 6, because we want to spice things up a bit. Now we have two classes. Perfectly fine. Two classes, each with a method, each with its own code. If we compile this, which we can do, which method would be run when we execute the program? There are a couple of ways you can answer that. One approach, well, maybe both get executed. I mean, computers have multi-threading, parallel processing and all that. I mean, that's why you have several cores, right? You can do multiple things at the same time, so maybe it's just executing all the methods. Yeah, maybe. This is a simple example with only two methods. It would be kind of weird if every single method in your code would get executed. Especially some methods require additional properties to run. You need to give values. So that is not the best approach. It's an interesting one, but that's not what happens. Hello, Kiro, Shift. Next approach. Maybe just go from the top. We just look for the very first method we find and execute that one. Okay. Usually C# programs consist of several different files to spread out the code a bit more, to make it easier to organize everything. In this example, maybe the first method, that's fine. But in a large code base, which method should we then use? What if these are two separate files? Two different pieces of a program? Then we don't really have a defined first anymore, right? We could go for alphabetical order or something, but that doesn't seem the best. Well, what other options do we have? Can't run all at the same time. We're working up to that. We're gonna write some in the code editor in a moment. What if we somehow told the system, specifically before we start, go to this one class, this one method, execute that? We provide the program a way to determine this method is where I want to start. I want to start at this method, or maybe at this one. When I run my program, start there. Well, that's one option we can do. Unfortunately, reality isn't so kind to let us freely decide that. With .NET, with C#, we have been given a specific entry point already. So instead of writing our methods and giving the system a clue where to start, we're giving the requirements to write a specific type of method with a specific name, and the computer will start there. And it's on us, the programmers, to adjust to C#. Not the best method, but it's not very uncommon. The same happens in other languages too. And this one method has a couple of requirements itself. One, the name. That might be the biggest requirement. The one method that the program starts with is called main. That's the first requirement. So when we start our program, the computer will look through our code and look for a method called main. But not just any main. Something we talked about last time. This method belongs to one instance of some class. So to run this method, we would first need an instance of some class. And how do we get that? What requirements are there for some class? Maybe there's a specific constructor in our class where the main method is, and we need to provide arguments, which themselves might need more complex initialization. So we can't do an instance-based method like here. That's our second requirement. Actually, let's keep that. Void could have been... No, let's put it in line. We use the static. So we don't need an instance anymore. Static void main. Like that. Now, the compiler can just compile our code, and when the executable gets started, the computer can look for a main method, check that it can just execute, because it doesn't need an instance, static, check. And because we kept these brackets empty for now, it's also not a problem with arguments it might need to provide. The only other problem we might have is, what is going on with this code? What would happen then? I mean, after all, these are two different classes. We can reuse the same name. We can also make this static. So, same problem again, right? How does our compiler handle this situation? It doesn't. This is invalid code. We can only have one main method in our code. If our compiler detects two or more methods that all fit the criteria set out by C#, static main method, the compiler just refuses to work. And therefore, maybe not the best approach with the main method, but that's just how C# works, and it's not too hard to get around. So, all we need is a class with a static method called main, and in there we can write whatever code we want. All the code we've used in previous lessons could be put into the main method, and from there we can then instantiate other classes, call other methods, run a larger program. And now finally the big moment. We're shifting over. This is an online editor you could use to write programs without installing everything, or anything actually. That's very important. Setting up a development environment can be tricky depending on your knowledge about computers and how comfortable you are with installing software. For now, at least, you can just use a browser, write code in there, get a feel for the language, try out some more advanced stuff. That's perfectly fine. Don't bother looking up tutorials how to install Visual Studio Code or Visual Studio, or set up another IDE and install the different compiler options and different frameworks and SDKs. Just don't worry about that for now. If you just search for C# online compiler, something like that, or interactive C# online, there are many, many different options. This one is not something specifically good or something, it's just the first in the list I got from the search engine that included a setting for the font size. So that was important for the stream, otherwise every editor will do. So let's maybe try to recreate our program that we've just written down here in the editor. Let's make that a bit bigger. I'm going to write a class. We call it some class. Brackets. And something you can see here, it automatically added the second bracket. These are a bit more advanced features that you get with a development environment. Most basic IDEs do include some comfort features. The bigger IDEs, of course, include some additional features that we're not going to touch for a while, because they kind of make learning a bit harder. The more work they take away from you, the less you get practice doing that stuff. Another reason why we didn't use an editor in previous lessons. Next, static void main. And again, it automatically added the closing brackets. And unlike my handwriting, these actually look nice. But in there, we did was int a equals 5. Another thing you can see here in the editor, that's very basic feature in basically every editor. We have this concept called syntax highlighting. It's subtle here. You can see class and some class. Class is a bit more bold. If you look at the lines of the letters, it's a slightly different font. And if you look at the number, it's a different color. Everything else is black, and this is a light, what is a turquoise, like bluish, greenish, something. There are other colors and font options, and the bigger the IDE, the more options you will get to make some crazy color combinations and whatnot. That's all to make it easier to read. This editor right now, still very tame, very basic. And let's also add the other class, since we're here. As other, even if it's not doing anything, let's just edit. Actually, that might be a good point to show this stuff. Let's write the other method also as main in static, so we can see the compiler complaining. And a6. So in this editor, I just press the big red button. Maybe not the best color choice. I definitely want to avoid that one. Screw that one. Here we get something nice. Compiler error. Well, it's not nice. As a programmer, this is the bane of your existence, but it's good that you see that in action now. So far, whenever I made a mistake in my code, you didn't notice, hopefully. But now I can't hide behind my handwriting anymore. The compiler will give me a nice little pat on the wrist every time I make a single mistake. And in this case, the mistake is that I have two main methods. Not allowed. So maybe just make main2. And no compiler errors anymore. It compiled, it ran, it just didn't do anything useful. Alright, let's remove the second class now. Let's talk a bit more about the main method. Right now, this is static, which was a requirement, and main, another requirement. The void, however, is not a requirement. We have other options. It doesn't need to be a void. I could also make this a main method with a return value. And so we return a value, maybe a. And honestly, I don't know how this editor... .7. Okay, I'm not sure what's going on here. Just to prefer 0. Yep, okay, so just set compiler errors. That's specific now to the environment you're working in. In case you didn't know, on basically every operating system, when you run a program, they actually pass a single value back to the operating system when they close. That's not something you usually see. You just see the program close and that's it. But the operating system receives usually an integer value from the program you've just closed. And that integer value can have meaning. the program can return a single integer value to declare, for example, an error code. To give a reason, hey, I closed because I had a huge problem that I couldn't solve, so I just shut down. Here's an error code that someone could use to figure out that something didn't work out. And most of the time it's a positive value, just being a message of, hey, I closed and these are some additional informations. I closed because I'm done, or maybe I closed because the user decided to close me. Just information that might be useful. And negative values would represent an error. That's just a common way programs handle that. That's not a requirement, that's not necessary. In any case, if we declare this method as an integer return value, we can provide the exact integer that the operating system would receive when the program exits. And 0 usually means just everything is fine, and in this case it seems everything not 0 is interpreted as error. Not sure about timeout, but that's how the online compiler editor determined to do things here. What about this part up here? I said we have an issue if this method requires parameters. If there are any arguments this method would need to run, well, our program would need to provide those values when it starts. And where does it get these values? If it's just starting and we don't have any variables yet, no code that can provide any variables or values, where could we get values from? So naturally we have to assume that the main method doesn't receive any arguments, right? But that's not true. Because you have a way to pass on arguments to this main method. The program has a source for that information. That's something else you might not be aware of depending on how much experience you have with computers. Just as how programs can have a return value on the operating system level, they can also have parameters you can pass on to them. You have command line arguments. Maybe you've at some point opened a link or shortcut to a program and saw in the settings that there is, after the full path to the executable, some argument like a dash no window, I don't know. Those were command line arguments that allow you to pass on values to the starting program. And you do that in form of string, in form of text that has to be interpreted by the program. Which brings us to a big topic, which we can now finally talk about: text. So far we only work with data types that store numbers, that can store true or false, or that store reference to other custom types that we defined. There are two very basic types we haven't discussed so far, because we weren't in a position to talk about them. And those two relate to text. Well, let's go back to the view here. If we wanted to store some text, A, B, C, D, E, let's do it like that. How could we do that in a computer? With a number, well, at least with integer numbers, that's pretty straightforward, right? Just we represent this in a different base system. It's 1, 0, and suddenly we have a pretty easy way to store that in a computer. This is a 1, this is a 0, this is on, this is off. We can directly store that in memory and that's it. Done. Text is a lot more complicated. In the end, these are just small graphics, symbols that we decide to draw somewhere. And those symbols have a meaning. And These are just some very simple Latin alphabet letters. There are also a lot of special symbols that don't relate to language directly, to text at least, to reading and writing, but that are still important. Think of all the different characters you have for math. Think of other languages. There are even special symbols that are categorized as text that are just for drawing. If you think of a smiley, well, they are usually already integrated into the system as text. You don't send someone an image anymore, you just send them a code for a smiley, and their system will interpret that code and draw a smiley. To handle all of this stuff, there is a very important standard called Unicode. And Unicode is a large organization, let's put it that way, that organizes these different symbols that you can draw, and it arranges basically a standardized table that's internationally accepted and used by basically everything nowadays, where each symbol you can draw is represented by one number. So let's simplify this. This is not Unicode right now, but let's simplify this to this maybe. Each letter we have has one number. And so when we store text, we don't store the symbols themselves, we just store the information that we need one of these symbols. We just store the numbers. What's happening before the main method gets called? We're getting into territory that I myself am not familiar with. First of all, depending on your specific settings, the JIT compiler gets compiled. The JIT for JIT, just in time, which is responsible for taking your intermediate language and then converting that to something your machine can execute. That's the framework basically that's doing its job. The specific initialization, there are some other things that happen, of course, in your code. Things like static constructor and initialization of static variables in some class, preloading of methods. There are a couple of specific details that I don't know too much about. A few things like the static constructor and the order in which variables are initialized, and things to look out for when writing complex classes, especially when you have statics. That's stuff we will talk about at some point. I'm not sure when, because that's a bit more advanced, and for normal programming you don't think about that until you get an exception and don't know how to fix that. Exceptions themselves, we haven't talked about exceptions yet. I have to put that on the list. I'm sorry, Kiro, but that's not something I can really help with. I'm not a C# expert, unfortunately, not yet. That's basically so steps in C# itself would be initializing variables. Not variables, sorry. Should be more specific here. Initializing fields. Then static constructor. Then when we call the main method, we would check which other method references it would use. Then look up reference methods. Load necessary assemblies. Because C# is lazy, it might not load all the data it actually needs to run your program. It's only loading one part of it, and then every time. Okay, one more. Load. Solo assemblies. And at the end somewhere call main. Well, then itself, these steps also happen right here, because these two steps are actually something that happens in every method. Because every time you load a method, it actually has the system has actually ensured these two steps have happened at least once before. Just the laziness of C#, which gives you improvements in performance in some cases, but just moving the work around. And these steps are basically happening every time you run any class methods. Let's remove all of that again. So let's go back to Unicode. So you have individual letters or symbols or something you can see on screen, something you can draw. And each one represents, or is represented by one number. And if you have a text, which is a combination of various different symbols, what you actually have in the computer is a combination of various different numbers. And the two types, we haven't talked about them yet. And one is these numbers, which aren't stored as simple integers. There's a special type for them called character, char. I'm professionally again the programmer, but there we don't really get to come in touch with this part of software. What language are you using? Are you actually using C# or C++? Or is it a custom script? Like, I think Godot uses its own language. Yeah, and the backend, C# and C++. Yeah. To be honest, I love the backend. I really like these details, how everything works. It's just really hard to get into. There's so much depth in the rear. And whenever you try to look up a simple detail, you're just... Ooh. There are so many other topics that suddenly branch off there. I spent, I think, a month trying to figure out some problems with COM interfaces and how C# handles COM and all that. That was a pain. I still don't quite understand it. At least I got my code to work, so that's nice. I mean, there are some good resources. Sometimes some developers on the .NET side do post articles and blogs, and they go into details in the backend. Those are actually pretty nice. Yeah, it's learning the framework. I think it's C# hides a lot. Like .NET, the basic framework behind, the one that's also running things like Visual Basic and F#, has a couple of features that you don't get to use in C#. Or things that are actually possible in the framework that's not possible in C# because the language hides that or does weird things to work around some issues the framework presents. Like if you see the discussions sometimes they have on new features and feature requests, those go in depth. Like there are people who argue about the very simplest things because they only look simple on the C# end, but in the backend that would require massive rewrites because of the weird ways the language handles things. Like how do objects work? What is an object header? How does it actually store in memory? How is the garbage collection keeping track of everything? Then you learn about things like weak references, like references that are not tracked by the garbage collection, and the weirdness that comes from suddenly having managed access to unmanaged code. But then you also learn about the performance side of C#. Like where do the official methods make a compromise and what can you do to work around that? And I love that stuff, but it hurts my brain sometimes. And there's so much to unpack that I honestly, something like how does the very first initialization of the framework and your program then work? I never really looked into that because I never needed it. I only know a few things like the JIT compiler. Oh, of course, you have also ahead of time compile. So you don't really use the JIT anymore, which then skips that part. That's with .NET. When you publish something, you can also make the ahead of time compile, which narrows down the target systems, but you get some performance again. Well, you get speed improvement at cost of memory, like always. Oh yeah, game engines. I mean, that's why the biggest engines are essentially also just a basic framework there where you rewrite the engine, right? I think, at least for Unreal Engine, as far as I know, the big developers that can afford that kind of development, that time sink, actually massively rewrite the engine and optimize it to their systems. And they really go down the layers. Actually something I don't really like. This layers upon layers upon layers and everything is hidden and worked on the framework. I really like working very close with the bits. The closer I get to actually manipulating bits, the more happy I get. Because I actually know what's going on and I have full control. When I have to call a framework that calls another library, that makes some injection into some other assembly, that indirectly calls through a pipe, a system, how can you properly debug that? You never find you can never fully get rid of bugs because there's no way to fully find them anymore. You can never be sure where the data comes from and where it's going. Yeah. Game development is its own pain. I'm glad I have not that level of complexity in my work. I still get to work with data. But digressing again, let's get back to characters. So char is the special type we use for storing characters. Each character is simply an integer with exactly 16-bit. And you can think of it like a short. It's similar to a short, also 16-bit. Well, U short maybe, unsigned. And 16-bit is not enough to store every symbol. Let's get maybe a bit into Unicode. The basic Unicode system would require a total of 21 bits. So right now, Unicode, the official table of numbers and symbols, has 2 to the power of 21 different numbers and symbols with meaning. So Unicode. I might be messing up the terminology here. It's not really called symbols. Glyphs maybe? Like I'm talking about the stuff you could actually see, the thing you draw. Oh, that's technically also not true because Unicode also contains control characters, so let's call it what it is. Code points. So each symbol, each glyph, each character, each individual text component that you can have that is represented by a number is called a code point. And each code point can be expressed by 21 bits or less. Our characters only store 16 bits, so we would not be able to store the full 21. But that's fine. C# uses UTF-16. The Unicode format. The UTF-16 means we have code points which can express by 16 bits or by 2 code units of 16 bits. What do I mean? For simple code points that fit into the 16 bits, we can use one character. That's fine. And for large code points with 17 bits or more, we use 2 characters together in a so-called surrogate pair. So basically we just combine 2 characters to one 32-bit sequence, and that is enough to represent one code point. So that's one character is a UTF-8 code unit. You combine code units to form a code point, and for Unicode, as long as you fit 21 bits, you have every possible code point that Unicode controls. So our letters here, A, B, C, D, are from the Latin alphabet, which are absolutely capable of being placed into a 16-bit number, because their code points are actually pretty low. I'm not sure what exactly that might be. Maybe 60? I think it was somewhere about 60, 62. Can't remember. But definitely on the lower end, we can't fit it into a character, so this would simply be these 5, not these 5 numbers, but these would be 5 characters. If you have something like an emoji, those are also code points in Unicode, like simple smiley emoji or something. That's a code point in Unicode. But they use a bit more. I think emojis usually tend to have... I mean, yeah, they would actually use 2 characters. What that means is, our text, even if it's a single symbol, like a single letter, might take more than 1 character. And of course, once we have a full text, we also need multiple characters. How can we store multiple values in one single block? We talked about that. It's an array. So char array, that will give us a text. The character is a single UTF-16 code unit, which can be used for Unicode code points, which represent different symbols and special characters and controls and whatnot. And so character array, a large block, a sequence of characters, is nothing but a sequence of code units, which is a sequence of code points, which is text. Unicode text. Unicode encoded text. I need to learn to be more specific, I think, but we're on a stream, we have time. And because all text always looks like this, it's always going to be a character array, there's a special type in C# that's representing text as a whole. And that's called string. Because it's a string of characters. Now, string are a bit weird. They do have the same quality as character and int and boolean in that they're very basic fundamental data type in C#. You automatically have them. They have their own code keyword, string. But unlike the other types, these are not single values you can just store in a few bits on the stack. These are just renamed arrays. And we've learned that arrays always hide on the heap. That means a string, make a string A equals something something, we get to that. This will not be a value on our stack, it will be a value on our heap. And A is just a reference to that. So string is not to be treated as a value type, but as a reference type. Think of string as a class, not as a simple primitive data type that would be stored on the stack as a value type. Right? Everything else is more like a struct. Fits on the stack. String is like a class, always on the heap. And characters and strings have some special symbols that we can use in our C# source code to make programming a bit easier. So character A. Well, I could figure out what code point that is and give it just the value, the integer value, but that's hard to use. So in C# we can use these singular quotation marks, these singular ticks. Important, these are not these slightly tilted ones. Like this is not either of these. Single quotation marks, just straight down, short line at the top, single ticks. And in here I can just type in A, for example. And the compiler will just figure out which value, according to Unicode, the lowercase a has in the table, and it will assign that integer value to A. I could, if I'm interested in that, go like this and store A into an integer. If you remember character, should probably shift this a bit to the side, sorry. Like this. Character is similar to ushort in terms of size. It's also just an integer value, not a floating point or anything, so it's no problem storing that in an integer. We don't lose any information. We can perfectly fit the entire information a character possesses into an integer. So we can just have it automatically implicitly cast. We could also, of course, explicitly cast it, but not necessary. And aint would now contain the exact integer value according to Unicode for lowercase a. We can also make calculation. We could also do this. One. Actually, I might be talking shit right now. Ah, right, forgot. Right. Actually, I should maybe get used to running my code before I say something like that. All right. Just want to make sure that I didn't get that wrong. It did cast implicit. But yeah, it would use the exact code point for lowercase a and add 1. And I could now char b is equal to aint, which wouldn't not work, because integer, 32-bit number, character, 16-bit number, we lose information, potentially, so we have to do that explicitly. But now, we have stored the value in character that's exactly 1 higher than the lowercase a. And because the Unicode table isn't just random, but actually has thought put into it, that happens to be lowercase b. By the way, something I've done before, but you probably haven't really paid attention to that. Slashes, forward slashes. If you combine 2 of them, you have a comment. We had that in our made-up CPU, in our fictional assembly language in the beginning as well. Just there it was single slash, here it's double slash. Anything I write after these 2 slashes is ignored by the compiler. So that way I can put something in the code just as a reminder. But yeah, this is b, lowercase. And I could make a character array now. Text. And we learned that. Make a new array like this, 2 maybe. 2 characters. And 0. Could assign this way. What about this? Never used this online editor, so I'm not sure which shortcuts it knows, and force of habit, of course I'm using my shortcuts, which translate to something completely different in this editor. So now we have text AB stored in this character array. And this is a bit annoying to write, so we use instead the specific data type string. Let's be creative, let's set text2. And we can use, again, special symbols to let the computer know we want to do text. And for a single character, that's a single quotation mark. For multiple characters, that's a double quotation mark. Regular quotation. Like that. So this text is just 2 characters stored on the heap, stored in the heap, and no special way for the compiler to handle that. Like, there are no fancy ways we can use this text, but it is there. If we use the keyword string, however, we can use it as a special type with its own rules. And so we can make our life a bit easier and say AB is a text, we just write that out, and the compiler will now ensure that AB exists as a character array on the heap. And that way we can easily write some text. So let's string text like this. Hello stream. Now let's say I want to interact with you a bit more, or with the user of the program. Hello stream, well, is inside the computer now, just as every other value we used so far was always just somewhere in the computer memory. What we've completely skimmed over in every single lesson so far, since we moved on from the CPU, is how to interact with the user. In our CPU, we had a simple register for input and output. C# itself, of course, has some more sophisticated ways to interact with the user. And this editor here, this online compiler, actually has some interesting features. It can also accept input. We're not going to talk about input yet, but we can use the output here. And how do we do that? Unlike so far, this output isn't an intrinsic feature to the language. There is no nice keyword we can use to send this text to the user, to the outside. What we have to do is actually interact with the operating system on a lower level. And luckily, we don't have to take care of that ourselves. Someone else went ahead and wrote the necessary code to do that for us. We just have to use that code. Why do we find that? Well, C#, if you set this up in your environment, will come with a couple of existing libraries. Libraries are just, like you imagine a library, a lot of books, a lot of information on all kinds of topics. And in programming, you have libraries that contain source code on all kinds of different topics. And you can just go ahead, pick a book you like, pick a class you like, a method you like, some overarching topic you like, get the library and just use that. You don't have to write that code yourself. And one of these libraries can be found under the larger umbrella name system. Now, system is not a class. We can use a dot here, but system is not a class. It's also not a struct or any kind of other structure you've seen before. System is just a name. It's a name someone has given to a group of classes and structs and other structures in general to make it easier to find them. We can do the same. What we have here is called namespace. And okay, can do namespace as well. Same structure as before, we just have the keyword and the curly brackets, of course. That was actually not right, like that. And we have to give it a name. And this name should, of course, be something unique or descriptive, just like with classes and methods. In this case, let's call it first program. This is now an overarching name. First program itself is not code. It's not a structure that somehow organizes the code in a larger sense. It's just that, hey, first program, that's the overarching name, and everything we put in these brackets here will always automatically get the name first program to start with. So this is now not some class anymore, this is first program.some class. And we can write another class other. This is now first program.other. Both of these are now automatically put in the namespace first program. You can also make another namespace. Second program class other. You can reuse the same name again, of course, because we're in a different scope. Different curly brackets, different code block, different scope. No problem here. This would be second program.other. So we have second program.other. Or we have first program.other. But because we ourselves are also, of course, in first program, so we can leave first program out. If we just write other, it will just look for the nearest other it can find, which is the class here. If I want this one, I do have to specifically tell it second. So that is namespace. No function in C# itself. It doesn't affect your code. It's only for organizing existing source code, because a large program might have millions of lines of code, which all have very different reasons for existing. And it's easier if you organize them into sections like, this is for the UI, this is the... I mean, we're talking about game engines in the chat right now, so this might be the physics model, this might be sound engines, and you all organize them in different namespaces to make it easier for the programmer to figure out what do I need, where do I go, which name do I use to find the specific things I need. And going back to this system, that's a namespace, an overarching name for a group of source code that is provided to us included in the language. Well, not language, included in the runtime, not the language. This isn't specific to C# anymore. String, static, void, these are keywords that are part of the language itself. System, this is now source code. This is not directly the language, this is using the language. This is source code someone else wrote using the same language as we do. So we can use it with the same rules that we know, but it's not part of the language itself. Right? So this is important to understand. Libraries you load are not part of the language. It's like Shakespeare is not the English language. Shakespeare used the English language to write some famous shows, some famous novels. Were they originally theater? Or were they just books? I don't know. Was Shakespeare originally just plays or was it books? Doesn't matter. Doesn't matter. But that's not the language. Just using the language, it's not the language itself. So these details can differ a lot. Two C# programmers can use the same language, but very different libraries. And even if they're called the same, they might actually work very differently. It's just that two different pieces of code share the same name, which isn't always good, but it can happen. Now in this specific library, under the name system, we can find a special class called console. Console refers to your console. If you open a program, you're probably used to UI. You see a window popping up or your entire screen gets filled with nice graphics. Those windows you see, those graphics you see, those are graphical user interfaces. But on a lower level, especially on old systems, you don't have directly a way to draw something on the screen. You only have a way to communicate with the user through text. You probably have seen some older movies where people just type in something on a computer screen and then some text gets printed out. Maybe it's fancy with a few lines, but that's all there is. There's no fancy UI where you can click or tap onto or whatever. And that still exists today, and it's very useful actually. A lot of programs, even current programs, are pure console. So the only interaction they provide to the user is through the text. If you think of servers, the stuff you use right now to watch the stream, in the backend doesn't need to have any UI. Why should the program on the server that's providing the data have any screen attached to it to show something? Like, there's no need for it. So the program doesn't bother with the resources necessary to draw something. It's just printing out some text if necessary for some admin to check that everything is okay, and otherwise it's focusing entirely on providing the necessary data. And so when you write a program, the easiest and most direct way you can do that is by writing a console application. One that's purely focused on interacting with you through text, which is very low on resources, very efficient, and it's also very easy to write because you only have to write a string of text out or read text in. With the user interface, there are a lot of complications and there are a lot of additional frameworks and libraries you have to learn to properly use UI. I'm not sure if I ever get to that in our lesson. But the console library that exists is basically everything you need to interact with the user now. Because console includes something like WriteLine, a method that's doing nothing else but taking a value from you, a text, and sending that to the operating system as feedback for the user. So we could just write some text in here. It would send that. Or we could use the text we've already written and write that. And if we execute that now, it got output to the operating system. And in this case, the operating system is, well, I'm not sure if it's running in WebAssembly on my end here or on the server somewhere. Probably on the, maybe not. Not too sure. But we've used the console output using this method to send text to the system where this program is running. And in this specific website, the output is then redirected to this part of the screen. On a computer, you might have actually a console running, like a terminal maybe on Unix or Mac if you have that open. On Windows, there are things like PowerShell and the command line where you can run your code. Or maybe you have an IDE which shows you the output directly. Like in this case, the browser shows me the output here, just for convenience. But this code is very simple, it's very reliable, and it will work on basically every system, because this idea of we have a console, write text is so fundamental to everything that we basically have operating system independent code right now. I can compile this for Windows, or for Mac, or for Unix, or for an Android, or iOS, or again, Toaster. It would work. Very basic. And so this is what we're going to use for the foreseeable future for giving our users, or us specifically, feedback for our programs. Let's do some more interesting stuff. Let's make a simple program, like in the good old days. Right? Simple program, we have two variables with two values, we add them together and store them in a third variable. What we can do now is a plus b equals, this is just text, keep in mind we have the quotation marks in front of back. You can also see syntax highlighting, all what's read as text is marked as red. So we immediately see this is text. If I leave this out, if I just write the text itself without the quotation marks, the compiler would try to interpret this as code, which is wrong. And we can immediately see that by, well, it being black instead of red. Now we know this is text, not code. And we can now add this text to C. What's going on? Shortcuts again, sorry. Force of habit. Now this is a bit weird maybe, we are adding a number to text. How does that work? I mean, for characters, that made actually some sense. Character C, character. For character, we already established that's just a number, right? So even though I have this letter here, I can just add 1. I mean, should probably cast it like this, but this is no problem. Characters are just numbers. So adding a number to that is no problem. But this is actually an array. This is a large block in the heap which stores several different characters. Do we add a value to one of these characters now? What's going on? Sometimes operators that you know have additional meanings that depend on which types we combine. We already talked about how adding to integers is technically a different operation than adding to floating point numbers because they work very differently, and so the computer would have to cast them into the proper value first. So int f equals c plus 1.0. So in this case we have a double. Actually you should give it the proper type. In this case it would cast the double, see the double and then cast the integer c first to a double, because that way it doesn't lose information, and then it could perform the addition, because right now it can't add an integer to a double. There's no function for it to do so. With a string and an integer, it works in a similar fashion. This add is not now switching from different types of data are added. It switches to a completely different meaning. But the basics still hold. We have a string on one side and an integer on the other. And there is no addition that combines an integer and a string, but it can take the integer and convert that to a string. So effectively, this will be the string 3 now, because A and B result in a 3. Like that. So what the computer will do is cast or convert our 3, the integer 3, to a string which represents the number 3. And I want you to be very clear about this. This is not the value 3 anymore. This is a text which has a symbol that we use to represent the value 3, the amount, the number. But this itself is not a number anymore. This is now an array, even though it's a single symbol only. It's still an array on the heap for characters, or for one character, that represents a graphic that we use to represent the number 3. Like, there is no 3 in this anymore. Like, we're very far away from the number now. These are no longer any numbers we can do addition, arithmetic, or anything. But now we have two types, or two values with the same type, and that means we can perform the addition operation. The operation has 2 strings, and this time it will do not an addition, because that's not possible for strings. It will do concatenation, which just means we take the first string and then take the second string and just mush them together. So, going back. When our computer operates on this instruction here and tries to run this code, it will see a string added to an integer, which doesn't work. It will then decide to cast the integer to a string, because that way it can keep information. In this case, a string to an integer, it can't do that. There is no cast, because the information doesn't exist. But an integer has a way to be converted, a very direct way to be converted into a string. So we just take the representation, the text representation of the value 3, which is this symbol. And then it has two strings to operate on, and it uses this plus sign to indicate the concatenation this time, which just puts the two strings together. Right, so this is what we expect the output to be in the console. Let's put that to the test. There we go. And if I change this to 10, this should be a plus b equals 12. Correct. And this is how in the future you can write little programs for your homework where you test your code by simply outputting whatever value you have with a bit of string attached to it. And that way you can confirm whatever is stored in memory. But wait, there's more. Let's say I want to output a few. I won't get rid of these shortcuts anytime soon. Let's put it like this. A plus b equals b plus a. With this, I can write two calls to WriteLine. As the name suggests, WriteLine writes in one single line in the output. So if I run this, I get this in the first line and this in the second. That's why we use WriteLine. It's very convenient. So whenever you write something, it will automatically jump to the new line, and whatever you write next will be on the next line. That way you can separate the values. I could use another command, write, that just writes the output directly without any new lines, and then it looks like this. So that's one way to do it. I could also do this. I can write in WriteLine, of course. Still the same output, because it first writes a plus b dot dot dot, then it writes dot 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 equals b plus a, and then it puts the new line. When I go the other way around, new line, and then just writes b plus a. And of course, this time, we put another one in here. We'll end up in the second line, unless I put another line here. So that's what write and WriteLine are for. Depending on what you want to do, one or the other. But something that annoys me here is I have to always write system.console. The console I can't really get rid of. Kind of, actually, but let's not talk about that yet. We can at least get rid of the system. How do we do that? Well, we go, let's put that in the usual place, which is above the namespace. Because what we're writing now is code that doesn't belong in a namespace. This is similar to namespace code that's organizing something, but it's not code itself. But we're organizing names. What we do now is using, which is a special keyword that also has some very different meanings that we got to learn in a couple of lessons, hopefully. System. So I put it just in the file like this, use the keyword using, and then the name of the library I want to use. Using system means that now in this file, our code will assume it's referring to system.something, if it can find it. So I can just remove this everywhere, and it will still work. If I remove this, and I just comment that out, it will have a problem because it doesn't know what console is. Put that back in. And now it knows, hey, console, I don't have it defined anywhere here, but I do have the system namespace, and there we have a console. So this is a very convenient way to handle external libraries. So usually when you write code, one of the first things you will see in a file is a bunch of usings. A single line of using for every library you use. Now things get a bit interesting. What if I have console class in my code. What happens now? Will this refer to this one? Okay, let's make class and a class. Make static, because we run directly in console. Void line string s but and do a second one. I'll never get rid of it. I'm always putting Control D down to double it, but well. So now we have our own console class and our own methods WriteLine and write. Which one will it call now? If it calls the system.console, it will output something. If it were to call our code, it will output nothing. Which one will it be when I press run? Surprise? It's ours. Well, not really surprising. We have a console, so of course we use that one. But we'll first check in our own namespace, first program, which is where console exists, so why bother looking anywhere else? Let's make this interesting. More interesting, namespace, name, whatever. Now we have a second namespace, exists in the same file here, with a console. Now it will of course use the system.console. It doesn't find console in here. So it's looking for another console, and instead of checking the other namespaces next to it, it will refer to the default namespaces it has stored up here. Check those. Well, let's make this a bit weird. What if I say using name? What will happen now? Nothing will happen. Stuff like this doesn't have a resolution. Your code will just not work. Unless you specifically write the name again in here. Now your code will know which which console to call. System. You might be wondering, does this actually make sense? Is this a realistic scenario? And the answer is yes. You will have cases where the same classes and methods and whatnot will be defined with the same name, but different meanings in different namespaces. And those are 2 namespaces or more, maybe 3 or 4 namespaces that you all need. Just that they have different purposes and they just happen to share a specific class name. And so for the most part, you can leave the name out because you use the using keyword, so the system will automatically know where to look for the console class. But then for the few situations where you have a conflict like this, you will have to add that manually again. Unless, and this is the last one for today, you specifically override it by saying console. When I refer to console, what I actually mean is system.console. So if I just write console, try to look for it in first program in our current namespace. If you can't find it, check for it in one of the usings. Except console, specifically console, has an override for system.console. So now, even though I have a conflict between system and name for the class console, it knows, hey, I'm using console from system, and I don't have to write the name anymore. It's a bit weird, and that might be a lot of abstraction you have to learn right now, but this is important because we are now going to start using external libraries, like system. And you will sooner or later come into conflicts and you might not be sure which using to use and where to use the full name and where not. These are ways you can handle that. These are the rules behind it. Just be aware, experiment, and don't get frustrated when the compiler complains about something. Usually it's easy to solve this, at least in the beginning. And with that, we're closing. As for homework, today we don't actually have homework, but if interested, just go online, try to find any online editor. And when you find, or maybe try several, just look which ones you like, which one fit your style, so to speak. Maybe try coding a bit. Try some programs. Most of them I saw already start with the first Hello World program, which gives you a boilerplate where you can directly start coding. And maybe try some of the code we used in earlier lessons. Try replicate something you did in earlier homework. And have some fun. Keep in mind, don't worry about anything on your PC, don't try to install anything yet. Just go to a browser, don't worry about anything. And with that, thank you for joining in. I'll see you next time.